We're looking at review worksheet 2 for 9.7 and 9.10. Number 1 says find a power series for the given function centered at the given value of a, in this case 0. So get the first 4 non-zero terms and the general term. So I highlight the general term because a lot of times students overlook this and forget about general terms. So I highlight it everywhere there's general terms. So that's something we need to go over and make sure that we don't forget to do. All right, so with these types of functions, we have three options. We can either build our Taylor rule, which is finding each of the derivatives and then plugging into the rule for Taylor, the steps for Taylor rule. Or we can go through long division. We can do 1 divided by 1 plus x squared and look for the what results, and we can get to the first few terms. Or we can, probably the easiest is looking for treating this as a geometric series. So the sum is just a sub 1 over 1 minus r. So if we see that this is something in the form that can be matched to the form of geometric series, that's probably the easiest thing or the most efficient way to go about this. So geometric series says that denominator needs to have a minus between the 1 and the ratio. So in order to make that a minus, I need my ratio to be negative so that I'm not changing my expression. So then if this is in the form now of the geometric series sum, then we know that the numerator is just going to be a sub 1, so that's the first term. And then each subsequent term, we're going to multiply by negative x squared. So 1 times negative x squared is negative x squared, times negative x squared is x to the 4th, times negative x squared is negative x to the 6th, so on and so forth. And then we just have to look at this pattern and create a general rule dependent on, now the general rule may look a little bit different depending on where or what value you want to start your n. Usually we start the n at 0, but sometimes starting n at 1 could result in a simpler or more elegant general rule. But usually you can just decide whichever n value you want to choose. And sometimes we look at 0 and 1 to see which one will produce the easier one, but you will not get incorrect if you decide to use 1 instead of 0 or 0 instead of 1 as the first n value. So in this case, looks like things will be easiest if we start n at 0. So negative 1 to the 0 times x to the 0 is going to be 1, so that's the first term. And then we move on to n equals 1. So n equals 1. This causes the alternating terms, alternating signs. And then x to the 2n causes each exponent to multiply by 2. Okay. So x to the 2n, if I plug in 1, it will give me 2. If I plug in 2, it will give me 4. If I plug in 3, 2 times 3 is 6. So a lot of times kind of takes a little bit of guess and check and trial and error to create a general rule that will allow for each of these terms to appear once we start the n in motion and we increase the n value by 1 each time. Number 2, let f be the function given by f of t, and g be the function given by g of x of the indefinite integral from 0 to x of f of t. Find the first 4 non-zero terms and the general term. So I want to highlight that again. We don't want to forget to write the general term. So looks like this is still in the form of a geometric series. So if we want to find the first 4 non-zero terms, we can think of the 4 as the first term, or we can factor out the 4 and then just deal with the 1 over 1 plus x squared. If we factor out the 4, then this looks exactly like what f of x was. So we can just follow the pattern, right? 1 minus t squared plus 8t to the 4th minus t to the 6th, and then multiply the 4 through. So here we have the first 4 non-zero terms, and then the general term, we know that we need an alternating alternator that will change the sign of each subsequent term. And then looks like it's going to be the same pattern, t to the 2n, but we just need a 4 out front since 4 is a coefficient for each of the terms. Part B, find the first 4 non-zero terms of the power series expansion of g of x. So power series means that we want to find the integral, indefinite integral of f of t. So we just have to find the definite integral of the result of what we found here. So if we evaluate the integral of each of these terms, 4 becomes 4t, negative 4t squared becomes negative 4t cubed over 3, 4t to the fourth becomes 4t to the fifth over 5, and then negative 4t to the sixth becomes negative 4t to the seventh over 7. I'll plug in upper and lower bound. If I plug in x, all the terms gets replaced with x. If I plug in 0, all the terms drop out. So here is my first first 4 terms. And then we have to create our general term. Notice that each term is alternating, so alternating signs. So we have negative 1 to the n. Look at the variable here. Look at the exponent. The exponent value is increasing, but they're odd numbers, right? So 1, 3, 5, 7. Easy way to create odd numbers is we do 2n and then do either 2n plus 1 or 2n minus 1. So we always, so to create odd numbers, we start off with an even and we add 1 to it. Notice the exponent and the denominator matches, so we can have the numerator and denominator match. Now, once you create your general term, it's always good to go back and double check and test out whether plugging in subsequent n values will return you these terms of your series. So we can test it out using 0 first. So negative 1 to 0 is going to be 1. 2 times 0 plus 1 is going to be 1. So 4 times 1 over 1. So 4x, that matches. Next up is 1. If I plug in 1, it'll give me a negative value. So that's where negative comes from. If I plug in 1, 2 plus 1 is 3. So there's where the 3 comes from. And then this 3 will match with the 3 in the bottom. And then next, if I plug in 2, I get 4 plus 1, which is 5, over 5. If I plug in 3 plus 1 is 2 times 3 is 6 plus 1 is 7, so 7 over 7, so that matches. So whenever you create your general terms, always good to double check and make sure that you're able to, whatever rule you come up with matches the series that you have. Okay, part C. Find the interval of convergence for the power series found in part B. So here we have the general rule, and then we can build this general rule to determine what the interval of convergence is. So we see exponents. Easiest way is to go about going through a ratio test. So ratio test is limit of as n approaches infinity for a sub n plus 1 over a sub n, and we want to make sure that it's less than 1. If it's less than 1, whatever the result is, if it's less than 1, then we know a ratio test proves convergence. And we can also, there's variable left over, we can then go to the next step to determine interval of convergence. So absolute value, so that means that negative 1 to the n can just drop out. We just have to add 1 to each of the n values, so 2n plus 1 plus 1. Here's a sub n plus 1 divided by a sub n, which is the same thing as multiplying by the reciprocal of a sub n. And if we expand this, we get 2n plus 4 plus 1. 2n plus 2 plus 1, which is 2n plus 3. And then here in the denominator is also 2n plus 3 times 2n plus 1. 4's cancel out. X to the 2n plus 1 cancels out with 2n plus 3 with the remaining of x squared up top. And then if we find the limit of this remaining expression here, notice the degrees match for the n's. So as n approaches infinity, this will just cancel out to be just 1. So we're just simply left with the absolute value of x squared. So absolute value of x squared is less than 1. If we put this in the form that matches, so x squared is less than 1. That's the same thing as saying x is between negative 1 and 1. Endpoints here do not converge. We have something that is in the form of a geometric series, so we don't have to worry about the endpoints. We know the endpoints will not converge.